So yesterday we first derived the equation for the conservation law, and from there, by considering this flow motion of ideal polytropic gas, so we derived the equations, so-called Euler system for compressible flow, based on three fundamental conservation laws, right? So what were they? There was conservation of mass, momentum, and energy, right? So for simplicity, we assume two-dimensional flow, but still the equation was complicated already, right? So in order to just simplify the problem in a way that we can handle, so we first remove the time variable from the problem so that we get the steady Euler system, right? And after that, in order to simplify further, so we assume a lot of conditions, such as the Bernoulli's law, so B equal to B0 for constant B0, and the isentropic condition, so entropy is a globally constant, right? And in that case, so we actually show that if the entropy is a constant, so we have isentropic flow, then the vorticity of the flow becomes 0, right? Which means that the curl of the velocity vector field is 0, so that we can finally represent the velocity vector as a gradient of a potential function phi, right? And then now we can finally write down the equation for this potential flow equation in the following. So where here gamma is a constant given from the problem. So physically it is called adiabatic exponent. So that is the equation that we derived yesterday. But most importantly, this is the type of this equation is not single. Actually, it is a mixed type. So this is the interesting point that we want to look further today, okay? So we are going to assume that the constant B0, which is a Bernoulli constant, is going to be just 1, just for simplicity. And for gamma, so gamma is just a given constant bigger than 1. And for simplicity, we are going to just look at the case where gamma equal to. So so this is the equation that we are going to focus from now on. So let me label this as the equation number 1. And then now let's just write this out in a more clear way. I'm going to write this in a component form. So which I will just leave all the detailed computation to you. So let me just write down the resultant form. So this one I can write out, okay. So actually what I want to tell you is that this is truly a second order PDE and nonlinear, okay? If you look at the coefficient matrix, so let me just say A11, A12, A21, A22. So we have to look at the coefficient matrix now, right? To figure out the type. So you remember what we discussed on the first day, right? So you collect all the coefficient as a matrix, and you compute the determinant, and then you look at the sign of a determinant. The sign will tell you the type of the equation. So that's the whole story that we are trying to do right now. So A11, so I'm going to just write out right away. So this is coefficient matrix. So this is a really huge expression. So let me just use the coefficient matrix A, okay? Okay, so simplified potential flow equation. Now I'm going to just assume that, so here, I'm going to just remove this term to be 0. So we only consider, so let us look at the type. So for that, we look at the product of A11 times A22. So if this A11 times A22 is a positive, then this is a simplified potential flow equation, which I will just use this initial. So this is, what is the type of that, if this is the case? So this is basically the determinant of the matrix, yeah? So if the determinant of a matrix is a positive, then the type of the equation is elliptic, right? So this is elliptic. And if A11, H2 is negative, then this equation is hyperbolic. And this is the case that we want to consider today. Really, what I want to do is to find a non-trivial solution for this equation so that the type of the equation becomes hyperbolic. But the interesting point is that you see the type of the equation is determined by solution itself. But theoretically, in order to determine the solution, you need to know the type of the equation so that you can analyze and find the solution. So this is a kind of a paradox in the study of nonlinear PDE. It's defined phi bar x1, x2, right? Because I'm generally considering two-dimensional problem. So let us define this as 2x1, which is basically one-dimensional solution of this simplified potential flow equation, okay? And then we call this one, so this is called a background solution. So the background solution, so from here, yields a hyperbolic PD, okay? But that's not, so we hope that try to find phi, this is a difficult part, sufficiently close to our background solution phi bar. So this is where whole story begins, okay? There's a find or solve the equation. So this simplified potential flow equation. Well, I'm going to use the same domain as before. So this is going to be a square. Okay. All right. So this is my domain. So here, gamma 0. Now for phi itself, I'm going to give the same value as our background solution phi bar, okay? But phi bar, by the definition, so here note that phi bar is just x1, so therefore on gamma 0, the value is 0. So just note, right? Because this is going to be hyperbolic PDE. So D1 phi, so same setting as before. So now this is important. Then now I'm going to give this as the same value as our background solution. But it's just the same. But it's going to give me the same solution, which is not interesting. So now I'm going to add extra one. So that's going to be h of a function of x2 here. Okay? So this makes the problem two-dimensional, not one-dimensional. Now I assign the slip boundary condition, so that's going to be d2 phi equal to 0. So here the main observation is that, so generally here h, assumption is that h is a smooth function. So this is a smooth, so infinitely many differentiable, and all the derivatives are bounded function. Moreover, now I want to give very particular one. It's norm C4 on 0, 1. So you remember less than equal to epsilon, where epsilon is a small constant. Okay, so 4. A small constant, epsilon. And then how small does it need to be? Well, that we can only decide in solving the problem. That's the difficulty, okay? But we will just briefly develop in terms of the perturbation term, okay? So now let us define small psi, okay, to be the difference between a solution phi that we want to find and the background solution. And then we are going to rewrite the problem in terms of psi. Okay? And for that problem as following, the main problem can be written in terms of psi as follows. So first of all, as a perturbation function, and then you can try to solve this one. So once you find the solution for this one, then you know psi, just put it back in here. That's gonna give you phi, which is the solution of the original problem. Yes? And it's the following. So heuristic observation. If so gradient of psi, so how do we put the size? We have to put the size at the C0 norm of a gradient of psi, right? If the size of this is sufficiently small, equation over there, right, is hyperbolic. And we know how to solve, at least if the coefficient is fixed, okay? So that's the first observation. So therefore, we try to solve that main problem by the method of iteration. So now I need to tell you what I mean by the method of iteration, okay? So this is where you need to know the theory for linear hyperbolic PDE. Let's iteration set. So that's going to look like something as follows. So I'm going to use the notation I. And that's going to be a set of functions, okay, which is the function from omega closer to R. And now I want to make that of all functions so that it's a norm, but I don't know what the norm is. That's the problem. Whatever the norm is, this is small here, okay? So here, sigma is a small constant. But I don't know what space to pick, so this is a Banach space to be determined. And how do I determine that? I can determine this by making a lot of heuristic observations. That's what I'm trying to do here, okay? So, and then this also concerns the application of this part by something that we can fix. So we are going to replace this gradient of small psi as gradient of phi for a fixed function in the iteration set. So let me tell you the strategy first, okay? So then A11 grad phi big psi, okay? Not small psi. So A22 grad phi D22 big psi equal to 0 in omega, okay? And then the boundary condition is going to be same. So on the linear boundary value problem associated with this big phi, okay? So for each choice of function phi from the iteration set, you get a linear boundary value problem. And before I get into any further, phi is sufficiently small. Boundary value problem associated with phi is hyperbolic. Okay, then we can solve. So then now, for any phi, one can find a unique solution boundary value problem phi. So this is where you use your knowledge from the first 2 days, right? Then we can define well, now let's try to connect this f with our nonlinear problem. So this is the really punchline. So if an element phi star satisfies that, so when you just map phi star by iteration mapping, if it turns out that this is phi star, then phi star really solves the main problem here. Mapping, right? The remaining question to solve this main problem is to prove whether your iteration mapping has a fixed point. So this is where you need to apply the fixed point theorem. And then in the word, okay? So this one says the following. Suppose that you have a mapping f. It's very simple. Less than 1, a constant, such that the mapping satisfies that this is less than or equal to mu phi1 minus phi2 in the space B. Okay. Then f has a unique fixed point. Less than 1, a constant, such that the mapping satisfies that this is less than or equal to mu phi1 minus phi2 in the space B. Okay. Then f has a unique fixed point. In B. Okay. So not only this guarantees that the mapping has a fixed point, in fact, the fixed point is unique. So if you can apply this contraction mapping principle to our problem, if that is the case, then not only you just to prove that your nonlinear problem has a solution, but also the solution is unique. So you can actually prove the existence, uniqueness simultaneously. So that is the really powerful point of the contraction mapping principle. So this is how the story goes in general in the nonlinear PD business. So whatever you do, always you start with this small perturbation. Then you set up this method of iterations. So then you have to make a choice on which fixed point theory to apply to solve the problem. The very first thing that you attempt is contraction mapping principle for everyone, because that gives you the strongest result that one can imagine. So you try. If you fail, because this can easily fail, because it's really strong condition to achieve. This is the problem. This is the nice property, but very strong. Strong is strong property to achieve. So strong, very hard to achieve. Yeah, that's like the two sides of the life, right? So if you want something big, you have to sacrifice big. So sometimes it works, sometimes it fails. In this case, works if you choose the correct choice. So somehow, the choice of a fixed point theory coupled with the choice of the Banach space in the defining iteration set. So they always go together. So it's not like a one-way traffic. So you really have to work from many. Safe trip back home. Yeah. So I hope you have a good time. Okay. That's it. Okay. Thank you.